the talk is called Unlocking the Next Wave of Streaming Applications, and it's really about, like Kostas introduced, it's about introducing new concepts that we believe are going to make it possible to actually model entire new applications as stream processing applications compared to what is possible with the state of the art. And that's not like state of the art in Flink, but in stream processing in general. So the set of stream processing applications did develop quite significantly over time. Ever since we started working in stream processing, it's come from let's say real-time approximate analytics over a lot of individual different new use cases to really very sophisticated real-time application use cases. And if you look at the broad categories of use cases that are being modeled at stream processing, it started out as something like continuous analytics, continuous processing, a bit of add-on to batch processing and so on, and really made its way to data-driven real-time applications to the point that stream processing has become a paradigm where applications and analytics kind of start fitting together as one unified big thing. And when we looked at how all these new applications became possible, there were always some things coming up in the technology that were the enablers of new applications. Very often it was just applications and APIs. So like the example Kostas mentioned before, when event time came up in stream processing, it was a big thing. It just made a new class of applications possible. It also made it possible to all of a sudden think of real-time data and historic or lag time data in the same way, which is a very important thing for a broader adoption of the streaming paradigm. Other things that came up that really where we saw new applications moving to stream processing, or in our case to Flink specifically, was the introduction of the state and time APIs, streaming SQL, complex event processing. Consistency is a very important thing. The introduction of exactly one semantics was a major step. Save points, so the ability to basically carry forward your application state when you actually evolve the application. So you can actually start thinking of the stream processing system as the ground truth owner of your data, of your state. Arguably, scalability was a big thing, especially for the very high-end users. The work that we did with companies to actually make sure that Flink runs, with thousands of parallel tasks and terabytes of state and so on, made these specific applications possible. And the often underrated but very important part of interoperability, being able to connect and deploy in ways that it can really interact naturally with all the other systems, and being operated in a way that it fits into a proper application architecture. And we're actually seeing that in all of these areas still a lot of innovation is happening. Partly evolutionary and partly revolutionary, like Kostas said. So in the course of this conference, you can hear quite a bit about, how streaming SQL is going forward, new semantics when it comes to joins in SQL that I find very fascinating personally. The combination of SQL and CEP into one system. Work on the scalability side, especially when it comes to timers, when it comes to dynamically adjusting, parallelism. This is actually the first conference, I think, ever since this the really big effort we did to re-architect the distributed deployment infrastructure in Flink. The Flip 6 effort has actually come to conclusion, so you can hear a little bit about what we can do now, looking at Flink both as a framework that where you have a cluster with which you interact with various jobs that you run, but you can think of it also more as a library, something you just put in a container and you throw out and run it like that. And what we're going to look today at is actually this fourth part, consistency. So we're in this space. We're going to talk about some new concepts we're introducing in this space today to move a few new applications to stream processing. And so consistency is something that is just absolutely essential for in order to build your applications, right? If you don't have consistency, you have to actually put a lot of logic into the application to compensate for that. And you can see this in the big trend of, key value stores started first of all to forego consistency, introduce eventual consistency. It helped scale them out at the beginning, but at some point in time, a lot of people just realized, okay, this is really, really hard to work with. Actually, everybody who's not super good in reasoning over all the possible situations and artifacts that can occur now in an eventual consistent system is basically going to write incorrect applications. So more and more these key value stores reintroduce strong consistency. And in a similar way, I would say, going from at least once to exactly once in stream processing, it was a similarly big step, and it actually made it possible for this thing to happen, that we're seeing quite a lot today. So instead of having applications built against key value stores, where you have a classic two-tier architecture, a stateless application layer, a key value store that holds all your state, and then you interact with the application in a request-response fashion. It works in the key value store. Basically, turn this whole paradigm around and just say, fuse both of these things, combine the state and the application logic into a stateful stream processing application, and just actually run your events through them. It's a paradigm that that just fits very well this idea of building applications in an asynchronous, in a reactive way, in a scalable way. The embedded state and application gives you a high consistency. It solves a lot of problems and gives you a lot of performance at the same time. Now that was a pretty big thing that happened over the last years, and we're working with a lot of users to implement this kind of architecture. Now it sounds very simple, but this transition actually means a big deal in many cases. But there are also a lot of cases that where we actually saw that users in the end were not able to make such a transition. And very often this actually was the case when we saw that what the applications were working against was not Redis, was not Cassandra, was not HBase or so. When the applications were actually working against a relational database, because what the relational database offers you is a little more than a key value store, where key value store actually gives you, as its name says, the view of a key and a value. The relational database has this interesting model of giving you more or less a more wholesome, consistent view with which you can more flexibly integrate over your entire data in your system. And maybe the most graspable example where this is really very different from what like key value stores and stateful stream processing today can give you is this particular example here. It's kind of the textbook example that is used every time somebody motivates distributed transaction processing, or actually transaction processing in general. For all of those in the audience that have actually done implementations with Flink, with be that the SQL API or the data stream API or so, just try to go in your head through this example. Try to build an application where you say, okay, I actually have some accounts that I manage in Flink, in Flink state. I actually shard them by account ID because I have a lot of them. And now I'm trying to transfer something from one account to the other. And let's say we're trying to make this a little more than the toy example where we say plus 10 here, minus 10 here, and so on. We're going to be good, but we do have to do it like the real way. We do have to check some preconditions. The original account may have to have sufficient coverage. It may actually be a bit more than just like checking this one account. You may have to, check the one account that you actually subtract from, but then you also have let's say the total aggregate over the accounts from the user that you want to check with. You actually do wire some money. Maybe wiring this money is just a condition for swapping some other assets. Let's say you're not just doing a transfer, but you're actually doing a trade. So together with the transfer, you're also swapping the asset that you trade. If you think about how to build this in a regular stream processor, you're pretty quickly hitting a bit of a wall. And in some sense, the essence of what is getting in your way is the fact that all stream processors today basically operate single key at a time. They do this correctly though. Like while you're operating with this single key at a time, you're under full correctness. Actually, much better even than what many of the key value stores offer you, but you're limited to one key at a time. And if you want to do slightly more complex operations, like in a transactional, in a correct sense, you have to actually interact with multiple datums, with multiple keys, with multiple tables even at a time. And that's just not possible in any stream processor. So when we're working on these applications, we're always hitting basically the same set of like requirements or the same set of limitations that we basically found in all these systems. So we thought to ourselves, wouldn't it be great if we actually could get stream processors to the point that they could actually access and update multiple keys at the same time, multiple rows. Think of an event comes in, and instead of doing just key by and working with one state, you can key by and work with multiple states at the same time. But while you're actually doing this, what you do is you maintain full transactional correctness across all the operations that you do, as if you're working just by yourself. No parallel operation can interfere with this. If you're coming from the world of databases, if you're a database developer, this is exactly what databases have under the umbrella of this whole transaction isolation theory, where the different levels of isolation are read committed, repeatable reads, cursor stability, serializability, snapshot isolation, and so on. And in order to maintain basically the same semantics that we give with a single key, what we'd have to do here is give something like serializability as an abstraction, or like an isolation level. At the same time, again with a bridge to the world of database systems, it wouldn't be enough for many applications to just work on one state or one table at a time. But you'd have to actually transactionally operate across multiple of these tables at a time. And of course, because there's very often not just one stream or one application that interacts with all your state, make this actually shareable between multiple streaming applications at the same time. And again, maintain all the correctness guarantees while we're actually doing this. So that was kind of a set of requirements that we found again and again. And initially it seemed like a very hard thing, but we spent some quiet time with Flink and actually came up with a really interesting way to solve exactly that problem. So what we actually do today is we announce the very first system for serializable multi-row ACID transactions on streaming data, a system that gives you exactly all those properties, basically doing transactional ACID processing across streams with tables, multiple rows, multiple tables shared across streams, all with full serializable guarantees. And it's maybe worth pointing out that this is more than a bunch of very, very famous databases give you, and it still performs better. So that's something we're actually really proud to be able to announce today. We call it the Data Artisans Streaming Ledger, serializable ACID transactions on streaming data. So just as a quick recap, what does that actually mean? So for all of those that where it has been a few years since their database lectures in university, ACID is this concept of transactional guarantees that you have while you're interacting with tables, or with tables in your database. So you're guaranteeing atomicity when you're doing an operation, and you have some preconditions that you evaluate on different rows or so, or on all of these rows together. And you decide to actually not do the transaction. You're guaranteed to not have any partial effects. So transactions execute either fully or not at all. Consistency, meaning in our example, going back to the wiring or transferring some money and swapping some assets example, it would actually mean that at every point in time, with all concurrent transactions happening, you're still leaving everything in a consistent place. So if you've defined your preconditions correctly, you cannot have ever a database coming into, or in this case, a state coming into like an incorrect state. So let's say an account going below a threshold of negative balance or something like that. Isolation is arguably the hardest one of all of those to realize. That is, even though we're in a distributed parallel system, we're running this with multiple threads, we're running this with multiple machines distributed across different computers, different regions. even with this distribution, with all of these transactions running in parallel, you maintain the correctness as if every transaction was just running by itself and nothing ever would interfere with it. So in our case, the isolation is the highest level of isolation that it can possibly give. It's serializable isolation level, which is pretty strong. Isolation has been traditionally the hardest thing to do, and this is why isolation has often been somehow weakened in order to ease the problem and give less guarantees. But we actually decided that we want to go for the highest isolation level here. And durability means that the transactions actually, once you've actually performed them, they're not going to get lost. So on the right-hand side, you see very roughly how this thing is abstracted from our view. It's not really, like trying to rebuild a database system and then exposing that together with Flink, but we're building this really after the streaming paradigm. So the way you model this is by defining a set of states and tables and so on, defining transaction functions, like you would define process functions, flat map functions, window functions, and so on in stream processing. And all these functions can basically interact with all of these tables, can access various rows and so on, and they just react to events that come in. So it's pretty much a stream processing application like any other, only that we slightly change the state abstraction to actually make this possible. And yeah, in my personal opinion, this is actually like a very nice continuation of what we've seen as the evolution of stream processing with respect to correctness guarantees. So going back a few years, at least once guarantees with the standard approximate real-time analytics, you wouldn't have data loss, but you also wouldn't have correctness because you could get duplications under failure cases. Like we said, exactly once was a very big step forward. It was basically what I think brought stream processing to a broader audience, because all of a sudden it's a system that actually computes correct results, which makes a big difference. And in the same way, as exactly once, guarantees basically started to give you correct results, but for a limited scope of applications, basically for applications that operate on a single key at the time. These, like the next edition, asset guarantees actually gives you correctness guarantees while operating on like multiple states, multiple tables, multiple rows at a time, and even shared state. And this also, if you think about the relationship between computation and state, this very nicely complements the landscape of compute and state. So we very often talked about like stream processing and key value stores and databases, and I think there's a very nice relationship between those, right? So if you look on the storage side and you think of the abstraction single datum or single key at a time, this is basically the space that key value stores have filled for a long time. And to in some sense, the extension of this to computing or stateful computing is exactly one stateful streaming as we know it today. If you actually look in the storage dimension beyond a single key or a single datum at a time, but if you look at a consistent total view, this is basically the domain of relational databases. This is what key value stores are not built and not possible to give you. And the extension of this like consistent total view of your data into the stateful computation space is exactly this concept that we're introducing today, the streaming ledger. If you're using this as a Flink programmer, this is pretty much it's pretty much built to feel very natural for anybody who's actually used Flink and stream processing before. So the transactions are all defined as functions that interact with the tables. And again, drawing a parallel to the database systems, you can think of this almost as you defining your transactions as stored procedures that you load into the database, and these stored procedures can interact with all the tables that you defined in your database, and they can operate with multiple of them. They can do multiple operations on a single table, multiple rows, multiple keys, and different rows and different keys on the other table, and so on. So they're very flexible in the way they interact. And each of these transactions is, or each of these, transaction functions is always triggered by an event stream. And again, drawing the parallel to the database systems, if you have the stored procedure that rests in the system, there are databases that expose triggering these stored procedures that execute the transactions by RPC. And this is somewhat the natural extension of this to the stream processing space, right? Rather than triggering an individual transaction with an RPC or so, you actually say, we have our event streams. Our event streams, an event is this nice thing that is like a piece of data and a trigger at the same time. And we just connect our transactions to these trigger events that carry the information to execute this transaction and let it run. How this exactly looks in the APIs, if you actually start to use this in code, I'm not going to have the code on the slides here because I think that would go beyond the scope of the keynote. But there's a talk later today by Igal who will actually walk you through a very concrete example of the APIs. How do you define the tables? How do you define the transaction functions? Connect them and run all of those things. And you can actually use this to build very nice use cases. So the first one, the kind of motivating use case I used here at the beginning was actually doing something like trade processing, right? So you have a set of accounts which hold the users and the balances, and then you have an asset ledger, something that holds where is under which account or which user owns how much of this particular asset or that particular asset. And you can actually run various kind of transactions over this, just lookups of the individual. You can have events that just look up state in the table and produce an output stream just with the results of that. You can have events that just modify the tables by depositing something, or you can run transfer events that trigger functions that actually atomically swap assets and move cash between the different accounts. And you can actually extend this to something even more sophisticated. So this is an example built after what we see happening a lot in the field of investment banking, real-time position keeping for risk management and reporting. There are all these individual parties creating certain events that are operating, let's say, on a localized view of their data. Because there are multiple reasons why they might do this. One thing is performance, one thing is compliance and isolation and so on. And they're creating all these events, and sometimes there's some implicit relationship between them, but you can't resolve this actually in the individual fronting applications that create these events. And then you have a separate system in the background that takes all these events and builds a consistent consolidated view across everything that actually holds the ground truth, that actually maintains all the positions. Or that maintains the position with all the equities and with all the cash you own across different accounts and so on. The way we implemented this is actually not by saying, okay, we've modified Flink in a heavy way and we've built a completely new version of Flink now, but we've actually built this as a library that just sits on top of Apache Flink. So that has a few really nice properties. And the first one is that once you have actually Flink, you start using this thing, you just add it to your user code, and you can actually start building these kind of applications. The second thing is it composes super well with the existing Flink APIs. You can just use streams that you derive from Flink streams from the existing connectors. You can actually mix and match this with SQL. So what you could actually do is you can actually say, you're running a position keeping system here, and the resulting events that basically tell you, okay, this trade actually resulted now in this trade actually went through and it resulted in a position update like that. You can actually just feed this into a SQL query within the same program that then gives you statistics over time, how things develop and so on, which is really nice. It supports save points just in the same way as Flink supports save points. You can actually at any point in time snapshot the application, store that, and restart it back with full consistency. Okay. I've talked a lot about how this whole thing is actually, what this gives you, what kind of use cases this solves. Maybe a few words on how this works would be interesting, because it seems quite different from what existing systems do today. And there's quite a bit of interesting secret sauce in this implementation that we're kind of proud of. The first thing is, it's definitely not built by just putting a relational database in the middle and then having all the stream processor and functions also interact with that database and running transactions there. That would basically just be a way of repackaging the existing architecture and say, okay, no, we hide these things behind the Flink API now, but it wouldn't really give you the properties that we want to have out of this. It wouldn't give you the properties of really high scalability and the ability to use save points and all of these nice goodies that stream processing offers together with this technology. So instead, this actually uses a pretty unique approach, I would say. To the best of our knowledge, we've not seen this approach used anywhere else before. And there are quite a few ingredients in that. The most important ones are actually the use of iterative data streaming. As you know, Flink actually has an iteration API. We kind of reworked this a little bit internally for this ledger to give it slightly different properties, but it's built on a very similar concept like iterative streaming. It uses a very unique form of logical clocks to basically coordinate the transactions between the different nodes with very little communication and very little interaction. And it makes very heavy use of Flink's event time and out of order processing capabilities. So without going into too many details, let me just show this part here. The core idea is to actually execute all the execute all the transactions in such a way that they result in an inherently conflict-free schedule. If you're familiar with database systems a little bit, there are two big families of, let's say, of transaction processing technologies. One is based on locking, or in the distributed database, based on distributed locking. The other technology is based on timestamps. And the locking-based implementation is often called pessimistic concurrency control, where whenever you basically, certain transactions have to wait on certain locks to make progress. The other one's often called optimistic concurrency control, where transactions mark their data with certain timestamps, and towards the end of the transaction, you kind of look for conflicts, and you may have to undo and retry some of the work. Now, what we're doing here is actually different. We have some really unique properties in the whole design of this, and that is by virtue of doing this in a stream processing fashion, right? Of not having to wait for a client that is connected and may send another SQL query or not, and we can't really know what is going to happen. By virtue of having all of these transactions defined as functions in the database and being triggered by events, and by having the liberty to kind of reorder these events a little bit, we can actually come to a point that we say we can always reorder them in such a way that it results in an inherently conflict-free schedule. So we're never going to read or write data that would actually be stale, that would violate the consistency guarantees. So what actually happens is when these events come in and you have the different transactions, let's say the one transaction comes in and says, hey, I'm going to read rows A, B, C, and I have to write back row C. And let's say the other one reads the same rows and has to write back A, and then there's another transaction that operates on some completely different rows. There's first of all a distributed agreement on what do we want as the results of this transaction schedule, and then it basically builds on top of, like I said, and on top of Flink's event time processing and out of order processing and reordering technology to actually look at these conflicts and simply reorder events, schedule them back for later, and so on, such that the resulting access schedule is actually conflict free. And gives you these serializable isolation guarantees. So as with all these technologies, there's probably a question: how does that actually perform? This is all nice and good, but is it actually useful in the sense of can it actually handle significant problem sizes? And There's a caveat to the next slides I'm going to show. These are really early results. The first version that we implemented here, we focused very much on just, first of all, realizing this idea, and second of all, making sure it's actually correct. So correctness was the first step here. This is not in any way performance optimized yet. So take these slides with a grain of salt. They might actually get better over time. But even the first version shows some really, really interesting numbers, I say. So this is a chart basically on scale out scalability. So as we add more threads, how many transactions can we actually get through per second? The experiments here basically use two tables, each table with 100 million entries. And runs basically the example that I used for motivating before. It transfers some values between two accounts of one table, and it swaps assets in the other table. So basically, every transaction that we do here is an update transaction that modifies 4 rows. That's probably worth noting, because if you look at many of the benchmarks for transaction processing against databases, it's always like 15% update, 85% queries, and so on. So this is actually the harder case where we say 100% updates. And we can actually get this system to do round about 2 million update transactions per second using a setup of 32 cores with this, with the initial implementation before going into any performance tuning, which is, I think, a very nice result for a distributed setup. 32 threads is not very heavy, and 2 million transactions per second, I think, is in a pretty good league, especially if you compare to relational database systems. The other question for this kind of transaction processing would be, how does it actually behave with accessing contended keys, contended entries in the table, right? And that's probably even the more interesting one to talk about, because the semantics of the system giving you always a completely consistent view across your multiple tables and so on. It doesn't mean that there's inherently some dependencies between some transactions that run. So while one is in the middle of doing something, you cannot necessarily start all parts of the other transactions, because it really strictly depends on the result of the one before. If you wouldn't actually make it depend on the results of the transaction before, you'd actually get incorrect results. So there's some inherent dependency, and as you get more and more of these dependencies, you reduce the amount of opportunity to parallelize the processing. And this is actually what this next chart is about. So we're actually testing different types of implementations, or different types of queries. On the very left, just queries that only read values, so there's no updates happening. Then reading and writing data, where we basically access keys between the queries so that each query operates independently. The next one, where we have a moderate amount of collisions, we just randomly let the keys overlap between the transactions happening, going across the tables with the 100 million rows. And then on the right-hand side, we actually try to do like a bit of an artificial case. We created these really big tables, and then we said, okay, let all transactions just operate on a super small subset of the keys. Basically, let most of them touch the same keys at the time. And this does give you quite a bit lower throughput, which is to be expected, because, like I said before, it reduces the potential to actually parallelize operations. But there's also some really interesting result in here, because this case is so extreme that it is actually crafted to kind of make systems fall over, right? If you look at systems that do optimistic currency control, once you get to these extremely contended cases, they tend to go to the point that they spend all their time just detecting conflicts, rolling back, retrying, detecting conflict, rolling back, retrying. So you can get them to a point where they basically don't get anything done anymore. And we're not getting this here, because we never actually have to abort and retry. The only thing that we do is we have to kind of reorder and serialize a little bit more work. So that's actually also the nice part of it, right? You'll actually get a regression in performance, but you'll actually never get to the point that you fall over, which is a really nice property of this approach that we've implemented here. All right. Just in order to show you that this is not not just something that exists purely as slideware, but that we also implemented something, then we actually take a quick look at actually a setup running here. And these things are a little hard to demo because it's a system in the background that's pumping transactions, right? How do you actually visualize that? And so we thought if this is actually something that makes it hard to visualize, can we at least make it a really interesting setup? And we thought, it's the age of the cloud. It's the age of where it's so easy to get computers all around the world. So let's actually look how this whole thing fares if we actually run a globally distributed setup. So let's actually see how it works if we let the thing coordinate some transactions between Australia and central USA, or some transactions between Europe and Brazil. So let's actually run them not within one data center, but let's just spread it out over the entire world. Now, why is that actually interesting to look at? And the main point is these transactions processing systems, they tend to be very sensitive to communication latencies, right? Especially if you go into distributed locking and so on, distributed also timestamps and collision detection and so on. It really depends a lot on how much overlap do you get, how long does it take to acquire a lock, to communicate a lock, and so on. So once you start actually doing them in a more distributed fashion where latencies get longer between the different nodes, they tend to just vastly degrade in performance. And we're just curious how susceptible would our implementation be to such a geo-distributed setup. And yeah, that's actually what we set up here. So now, just to put these numbers that we're going to see now in perspective. Sorry, I have to go to the latest slides again. If we look at this particular, chart here. Any second. Right. If we look at this particular chart here, and you actually do the math a bit, we're doing 200 million transactions, 32 cores. You can see that each individual core pushes about 60,000 transactions per second. Now, just bear that number in mind, 60,000 per second. And that particular setup was done, in a single data center. All these nodes are very close together. So let's actually look at this particular one now. So it's a smaller setup. We only have 10 nodes. If we look at the task managers, you can actually, we've built it somewhat into the names. I'm not sure how well you can see this from the rows in the back, but there's some in Brazil, there's something in Australia, in the US, in Belgium, Japan. If we look at what the job now does, this is basically the job graph that comes out of this system. And if we look at, let's just look at the throughput metrics. So let's look at the metrics of the transactor. What it shows us is that each individual core, so this is like a metric of one individual instance, each individual core is pushing around about 20,000 transactions per second. So it's a bit less than we get in the single data center setup, but it's only going down to a third by going from a single data center setup to a complete geo-distributed setup. Now, I would, if you've actually got access to some expensive distributed database from Larry or from whoever, try to do such a setup and try to run your transactions like that. I'd be very curious what results you get. I would venture to say that this is a pretty good result for going from a single data center to a geo-distributed setup. All right. So concluding this, one thing I do have to say is this whole technology is possible because Apache Flink does offer such powerful building blocks. It is implemented on top of Apache Flink 1.6. There were, I think, 2 minuscule additions that we actually made in Flink, which basically were just exposing something that we previously hid in the API. For example, in order to build our own flavor of iterative feedback and so on. And there's so much very powerful technology in Flink, continuous processing, the ability to do iterations, its flexible state abstractions, the asynchronous checkpoints, the sophisticated event time watermarking mechanism. And this is really what makes this technology, what underlies this technology. So kudos to Apache Flink as the heavy lifter on which we could build this. The whole system, we actually make it available as part of the Data Artisans platform River Edition. So if you go to the later talks and so on, this is a new edition that we're offering of our product. So it, in addition to the application manager, it actually gives you the streaming ledger, so the ability to run this consistent asset transactions across tables and streams. If you're just curious in prototyping something and seeing how this actually works for you, if it actually, if this abstraction fits your problem and so on, the API as well as basically a testing runner that is non-parallelized is freely available under the Apache license. So we're very happy to take feedback on that one. And yeah. For those of you that want to get more of a feeling, okay, how does that look like in code? Like, how do I embed it in my streaming application? How do I connect all these streams and transactions, define the tables? What can I do? And how easy is it to use? Come to the talk this afternoon at 4:10 by Igal Schielmann. He's going to give basically a developer-centric overview of all this technology. And you can, of course, always come to our booth to learn more. Thank you very much.